create a barrier and stop the things passing through. Let's get into particulate filtration. All right. What we're going to do is create a sieve. There's going to be a number of different ways that we're going to do this, but all we're trying to accomplish is make an opening that's smaller than what the thing is we want to take out of it. A 6 micron particle will not pass through a 5 micron filter. That makes sense. That's not rocket science, right? Everybody understands that. But so we're going to filter out by the means of direct intercept, but we can also filter things out by the means of bridging as well. Because a lot of these things, if I can stop it on the edge there, and I can create bridging, now even though I have particles that are smaller than my opening, I create a filter that will catch smaller things. The most effective filter, the most effective particle filter, is one that's been used for a while. Once I start catching stuff on the outside and building up a filter cake, it becomes a better filter because it's going to be able to catch more and more stuff on the outside. So it becomes more effective. What's the downside to that? Like Phil said, the downside for the customer is I start building up a filter cake, now I start plugging and I start back pressuring. So that leads to like what Derek's saying about I need to replace the filter. I have a great particle filter, but now I have a really low water supply filter. It starts reducing the amount of water flow that goes through it. I can do this filtration a few different ways. The first way that I can do this level of filtration is what's called surface filtration. All right? All I want to do is create a media, a surface that has little doorways in it, and then depending upon what the door size is, I can keep the contaminants out on the other side. Real simple, real straightforward surface filter. An example of a surface filter is like a Walmart on Black Friday. Right? You can only get so many people jammed through those doors at Walmart in order to go through and get into what's on the inside. And so the door becomes a real simple surface filter. It's the same principle. I'm creating openings to allow what I want to go through or to reject what I don't want to go through. A couple of versions of pleated paper. So just starting off with real commoditized filters. And surface filters are very simple, very cheap, very effective and inexpensive. We make a couple different means of surface filtration. We do it with pleated paper. We do it with other membrane materials that we use as well. But again, it's just a matter of creating a sieve and catching this material on the outside. That's surface filtration. Let's go to the next step. I want to talk about depth filtration. So depth filtration is a little bit different. Depth filtration, what I do is I create what's called a tortuous path. I create a tortuous path through the filter that catches a variety of different size materials as it makes its way through. What that does, it gives me a lot of capacity. Versus if I wrap a sheet of paper around a filter like this, the only surface area that I have is this area that's around the outside of this filter to catch it. Once I load that up, I'm done. I start back pressuring. A filter like this is designed so that it's catching the big stuff on the outside, but as the water makes its way through towards the inside, it gets tighter and tighter. So I'm catching contaminants all the way down through the filter. So I can get a lot better life out of a depth filter. Benefit here is that I can control my size a lot better. I can control what the filter size is here better. Here it gets a little dicey. It can get a little bit more challenging. Better control, less cost, higher capacity, better flow rate. Okay, does that make sense? Surface filter, depth filter. Let's talk about sizes, because I'm talking about a bunch of different things, particles and things that are in the water. What's a micron? Anybody got an idea what a micron is?
A measurement?
It is a measurement of length. So it's a measurement of length. You knew the answer, JP. Come on.
I don't know about that.
What's a millimeter? How big is a millimeter? Pretty small. It's about if you look at your pen, it's about the width of the tip of your pen. That's a millimeter. There's 1,000 millimeters in a meter. That's what that means, millimeter. There's 1,000 of them in a meter. Well, a micron is a millionth of a meter. So there's 1,000 micron in 1 millimeter. 1,000 micron in 1 millimeter. Okay, so it's a shortening of micrometer. Okay, so so what? What does that mean? Kind of like you, Derek. Like, yeah, okay, sure, you told me, but what does that mean size-wise? So let's get an idea what that means size-wise. If we go down to 1 micron, 1/1,000,000th of a meter, that is about the size of a cyst. Okay, a cyst. What is a cyst? Does anybody remember, has anybody ever heard of Cryptosporidium? Okay, back in 1993, where does Chicago get their water from? Where does Milwaukee get their water from? Lake Michigan. Cleveland, Lake Erie. Detroit, Lake Huron. Surface water. What's the primary contaminant in surface water? What kind of contaminant? Particulate. Including living organisms. Cryptosporidium is what's known as a cyst. All right. What are some of these living things that are in the water? Well, let's go smaller. Let's talk about viruses. Viruses are about if you go 1/10, about 1/20. So viruses are somewhere in the neighborhood of 100th of a micron in size. Anywhere from 100 to 500. So 0.01 to 0.05 microns in size is a virus. That's a living, it's not really, it doesn't, you know, it is a living organism because it can reproduce and grow and everything, but it's kind of its own unique thing. Bacteria are about 1/10 of a micron in size. So if you go 0.01 is a virus, 0.1 is bacteria. 1 micron is a cyst. Does everybody kind of have an understanding of what a bacteria is? Single cell creature, it's just prowling around looking to reproduce, right? Just kind of, hey, it's life, it's doing what it's doing. It consumes things, we need them. There are bad bacteria, there are good bacteria. Like coliform bacteria are bad, other bacteria are good. Bacteria are about 0.1 micron in size. So if we want to filter them out, what size filter do we membrane? So we need something that'll get down to 0.1 micron, about 1/10 of a micron size. A cyst, about 1 micron in size, what it is it's an organism that has it has a shell around it. And most of the time it sits dormant, it just kind of sits in the water, doesn't do a whole lot until it gets into an area that it wants to grow and reproduce. Warm, stable. Well, Cryptosporidium Giardia live in the lakes, and they are typically filtered out and treated for. We had an outbreak in Milwaukee in 1993. Cryptosporidium got into the water supply, and it contributed to a little less than 100 deaths. It's like 94 deaths in Milwaukee, just caused by the sicknesses of the cysts that were in the water. Good thing about a cyst is that it's about 1 micron size. So even if it's 1/1,000,000th of a meter in size, we can easily make filters that'll filter them out. So that's what a micron is. That's the size we're dealing with. Any questions? All right. Still, the main thing is all the things we talked about are still particles in the water. If I throw this out into Lake Michigan, if I throw a cine-mini out onto Lake Michigan and it's floating around and I need to filter it out, I'm still going to do it with a filter of some sort. I can do this with chicken wire, right? That chicken wire is going to have a micron rating. Probably somewhere in the 500 micron rating, something like that, 1,000 microns. But the main thing is, this bit of particle floating around in the surface water is no different than the virus or the bacteria or the cyst that's out there either. I just need to create a barrier that stops it passing through. So that's what we're going to talk about.